Welcome to the lecture on Engineering Statistics and Linear Algebra. In my previous lecture, I discussed about the continuous bivariate random variables and also about the joint PDF and joint CDF with respect to the continuous random variable. In this lecture, I am going to discuss about the discrete bivariate random variable and also about the conditional bivariate random variable. So as I told in the previous lecture, the joint PDF and joint CDF can be applicable only in the case of continuous bivariate random variable. As in the case of discrete bivariate random variables, we can use only joint PMF as well as the joint CDF. So first we will discuss about the joint probability mass function of discrete random variable. So the joint PMF of two discrete random variables, say capital X and capital Y, is defined by the P of capital X capital Y of xi comma yj will be equal to the probability of the random variable capital X will be equal to xi and the random variable capital Y will be equal to yj. So this condition can be used in case of the joint probability mass function. The properties related to the joint probability mass function. The first property is the range of the probability function, mass function, will be varies from 0 to 1. That is 0 less than or equal to P of xi comma yj will be less than or equal to 1. Next one, the summation, so summing all the probability values, so will be equal to 1. That is summation with respect to xi, summation with respect to yj of P of xi comma yj will be equal to 1. So next is the probability of the random variables x comma y will belongs to some event capital A will be equal to the summations of xi comma yj which belongs to the range space Ra of P of x comma y will be this condition we can use here. That is where the summation of over the points xi comma yj in the range space Ra corresponding to the event A, we can take it. So now let me see about the joint CDF in case of the discrete bivariate random variables. So the joint CDF of discrete bivariate random variables capital X capital Y will be given by capital F of x comma y with respect to discrete random variable capital X and capital Y will be given by summation of the random variable xi is less than or equal to the real number small x and summation yj less than or equal to small y will be equal to the probability of the xi comma yj, we can take it. So this is a condition we can use to estimate the joint CDF in case of the discrete bivariate random variable. So next is marginal probability mass function. So in case of discrete random variable also we can define the marginal PMF function. That is, suppose that for a fixed value of capital X is equal to xi, the random variable capital Y can take on only the possible values of yj only. That is when j ranges from 1 to n. So then the probability of the random variable capital X will be equal to summation with respect to yj, the probability of xi comma yj, I can take it. So to estimate the marginal probability mass function with respect to x, I can use this formula. So where the summation is taken over all the possible pairs of xi yj when that xi is fixed there. Similarly, I can take P of capital Y is equal to yj will be equal to summation with respect to xi, the probability of xi comma yj. So here I can estimate the marginal probability mass function with respect to y from this formula. So same thing here also. So here also I can use the pairs xi comma yj with the fixed yj I can use here. So next one is independent random variables in case of the discrete bivariate random variable. So if x and y are two independent random variables, when means the probability of xi comma yj will be equal to the probability of xi into probability of yj. So this condition we can use for to show that x and y are independent in case of the discrete bivariate random variable. So next is conditional probability density function. So in case of the joint distribution, we can use the conditional probability density function also. The probability density function is known as conditional PDF. So when one random variable out of two random variables as a fixed value. So out of two random variables, I'm going to fix one random variable as a fixed value. So there we can use the conditional PDF. Suppose we have two random variables x and y, and x is a fixed value, say the real number small x. So in this case, the conditional PDF of y I am taking. So if I am fixing the value of x, so I can estimate the value of the conditional PDF of capital Y. So that is the small f with respect to the random variable capital Y over the ratio y by x is given by the random variable, I mean the joint PDF of f of x comma y will be divided by the marginal random variable, I mean the marginal PDF f of x can be taken. So the formula will be like this: the function small f with respect to the random variable capital Y over the ratio y by x is given by the joint PDF of x comma y divided by the marginal function f of x. I can take it. So where f of x is nothing but marginal density of the random variable capital X. Similarly, so I'm going to fix y now. So if I fix the value of y, I can estimate the conditional PDF of the capital X. I can estimate, that is the small f with respect to the random variable x of the ratio x by y is given by the joint PDF of the function f of x comma y divided by the marginal function f of y. I can take it here. So next is the properties of the conditional PDF. The property number 1, the conditional PDF is non-negative function. I mean the function small f over the ratio x by y will be positive always, and also the function over the random variable capital Y of the ratio y by x will be positive. That is, as conditional PDF is a ratio of 2 PDF. So, and we know that PDF is a non-negative function. So from this condition we have the property number 1. The property number 2, the area under the conditional PDF is always unity. That is, the integration minus infinity to plus infinity, the function over the random variable capital X over the ratio x by y into dx will be equal to 1, and the integration minus infinity to plus infinity f of with respect to the random variable y of the ratio y by x dy will be equal to 1. The property number 3, the conditional PDF will leads to the marginal density only if random variables x and y are statistically independent, means we can have this condition. That is, the function small f with respect to the random variable y over the ratio y by x will be equal to the function small f of the random variable y of the function y. So similarly, the function the small f of the random variable x over the ratio x by y will be equal to the function f of x. I can take it. So we'll see how to prove this function. So we have the property like this, that is with respect to independent random. So if capital X and capital Y are independent random variables, so we have the property like this, that is small f of xy will be equal to f of x and f of y. I can take it. So I will call this one as equation number 1. And also we have the property like the function f of the random variable capital X over the ratio x by y will be given like of the ratio the joint PDF of the function f of x comma y divided by f of y we are having. So I'm going to replace this equation number 1 in the equation number 2. So I will get that function small f of x by y over the random variable capital X will be equal to the joint function f of x. I can take it here. So like this. So on replacing the value here, I can cancel the function small f of y and f of y I can cancel here. So I'll get f of x here. So similarly, I can prove the joint function, that is the function f of the ratio y by x with respect to the random variable capital Y will be given like the function f of y. I can take it from the same condition. I can use here also. So we'll see one example on the joint conditional probability function. So the function is f of x comma y is equal to 4 into x into y with the range of 0 less than x less than 1 and 0 less than y less than 1. So we have to find the joint conditional probability. So we have the formula for joint conditional probability like this, that is f of x by y will be equal to f of x comma y by f of y. So the function is given by 4 into xy is a function for f of x comma y. I'm going to replace here, and from the given condition, from f of x comma y we can estimate the value of the small f of y also we can estimate here also. That is by integrating the function, this function with respect to x over this limit, I can estimate the value of f of y. So I'm going to replace both the values here. That is f of xy and f of y. So I got the value like 4 into xy divided by 2y. So it will be equal to 2x, I will get it. Similarly, the value of f of y by x can be estimated from the formula, the function f of x comma y divided by f of x. So this f of x can be estimated from the f of x comma y by integrating this function with respect to y with the limit 0 to 1. So I will get 2x here. So on cancelling the function, I will get the value 2y here. So in the next lecture, I'm going to discuss few more examples related to the joint PMF and also on joint PDF also. Thank you.